Well, good afternoon, everyone, and welcome to this week's edition of our live astronomy program, helping you see outer space without leaving your place. My name is Justin. I'm one of the astronomers at the Science Museum of Virginia, and as always, I'm happy to be your guide. Also need to thank our sponsors for this series, Allianz Partners. Always great to have them on board. And as always, if you are willing and able to help the museum with our other continuing missions during this time, we'll have some links for you in the comments. Now, if you're just joining us for the first time, welcome. Glad you are here. But I do want you to know that you are joining a journey that is already in progress. We're kind of working our way out to the edge of the universe. We won't quite get there today, so you won't see everything. But if you want to go back and see the past episodes, they are, of course, saved right here on Facebook. You can take a look at that. If you've already watched those previous episodes, welcome back. I hope you're ready for today's step in the journey. The usual rules still apply. We're using the same software today that powers the theater at the Science Museum. It's planetarium software called Digistar 6. It can do some pretty cool stuff, so if you're able to watch it full screen on a nice big monitor, I highly recommend it. You'll probably see me looking at my second monitor from time to time, so I won't always be looking right at the camera. In fact, I'm going to get us switched over to the Digistar view right now, and we're going to start with a couple of current events. There isn't much more current in the space exploration world right now than Mars. It's Mars launch season. Every couple of years, countries have an opportunity to send their spacecraft to Mars, and this year 3 missions are planned to get underway, and as of about 12:45 this morning, 2 of those are underway. The United Arab Emirates Hope mission got started Sunday evening for us here on the East Coast. And then China's Tianwen-1 mission launched in the early morning hours today. So those 2 are on the way. Of course, we're awaiting the launch of NASA's Perseverance rover, currently scheduled for July 30th. And that just happens to be next Thursday. So we'll take a little deviation from our route to the edge of the universe during this show, talk a little more about Mars, these missions, why we explore it so much during next week's show. So stay tuned for that. Now, I don't have public tracking data for where the Chinese mission currently is, but I can show you how far the first mission to launch towards Mars this year has gotten. The Hope mission, already 5 days into its journey, is now outside the orbit of the moon. We'll get that on the screen for you. And there is the location of the spacecraft. Not drawn to scale, but that's where it is. Looks like it's made a pretty good start to its journey, but it's got a long way to go. All of these spacecraft launching towards Mars this summer, taking advantage of the planets being in rough alignment on the same side of the sun, but it is going to take them about 7 months to get there. I believe all 3 of these missions scheduled to arrive at Mars in February of 2021. So after the excitement of these launches, stay tuned for a long cruise to Mars, and then we'll get those landings and things like that early next year. So that's what's going on at Mars. Speaking of hope, we talked a little bit about exoplanets a few weeks ago, and one of the big hopes of exoplanet scientists is to find another solar system that looks sort of like ours. Multiple planets, maybe a mixture of sizes, some rocky planets, some gas giant planets around a star like our Sun. Might be a good place to look for planets like Earth, maybe life like us. And there's a little bit of news on that front. As of yesterday morning, astronomers have a first of its kind image. This is a star, very much like the Sun. It's got some background stars in that side of the image. But if we scroll down this direction, we see 2 more dots. And it may not look like much, but those 2 dots are both planets in orbit around this star. So we have a direct actual image of these planets, and it's the first time that pictures of such planets have actually been captured. So multiple planets around a sun-like star. The star has the rather unromantic name you're seeing on the screen now, TYC 8998-760-1. Means it's part of the Tycho catalog collected by spacecraft a few decades ago, but let's go take a closer look. It is about 300 light years away from the sun, and although it's about the same size and mass as the sun, one big difference between our two systems is that this one is incredibly young. This star is thought to be only about 17 million years old. All right, that sounds like a big number, but the sun is something like 4.5 billion years old. So this is significantly younger. So we're seeing planets that are in a little bit different stage of their formation. They're still kind of warm from heat left over from their formation. And based on their size and brightness in the images, we can say a couple of things about them. First, the inner planet is big. It's something like 14 times the mass of Jupiter. The outer planet is a bit smaller, only 6 times the mass of Jupiter. But it's the distances here that are really unlike anything in our solar system. Those two planets orbit this star at 160 and 320 astronomical units, respectively. So there's our solar system for scale. The Earth would be the third one there. That's 1 astronomical unit from this star, and these new planets, newly imaged planets, are hundreds of times farther away. So a historic image, an interesting image, but not really anything that is that much like home, despite the similarity in the stars. All right, speaking of home, let's head back that way and continue the journey we started last week. We were taking a look across the electromagnetic spectrum. Now, that's just all the colors of light that the universe has to work with. Our eyes can only see a small part of the electromagnetic spectrum, those colors you see across your screen now. But the universe has many other wavelengths of light, wavelengths of radiation, energies of radiation to work with. Lots of ways to describe these things. But there's one way that I don't think I mentioned last week. Last week, we kind of focused on the right side of this picture. We've had radio waves. I kind of skipped over most of the microwaves, but showed you some ALMA images. They're pretty close. Then we got into infrared light just a little bit. And another kind of secret here is that the electromagnetic spectrum and the colors of light we detect from objects across the universe also works a little bit like a thermometer. So when you pick up microwaves and radio waves, that's probably a pretty low temperature object, pretty cool object. There are exceptions to every rule, but that's a good place to start. Then when you pick up ultraviolet waves, Xrays, gamma rays, the kinds of things we're going to see today, we're generally talking about higher temperature objects or very energetic events in the universe. So that's kind of an interesting comparison, I think. And it can help us see some other relationships that I kind of brought up last week or have brought up in different shows but haven't really explained. And now I think I can explain it a little bit better. Here's another chart. We're comparing wavelengths of radiation across the bottom, just like the spectrum that was just up on the screen, and then intensity of that radiation. I know units and values aren't included here, but those are available on request if you want to know. So you see the visible part of the spectrum there, highlighted it with the rainbow again. And then this line is what we would call a black body curve. That just describes the way objects emit radiation in the universe. There aren't really any perfect black body objects in the universe, but stars and things like that are pretty close. And this is actually the curve that shows all of the radiation that the sun emits. And you'll see the curve is highest over in the visible part of the spectrum where that rainbow is. But you can think of all of the area under that curve as radiation of some sort that the sun puts out. Off to the right of that visible part, that's going to be the stuff we saw last week. Infrared light, microwaves, radio waves, and the sun emits all of those. To the left, you've got the ultraviolet, the X-rays, the gamma rays, and the sun can generate all of those as well. We see most of it in the visible. In fact, most of the sun's visible light is right in the middle of the visible part of the spectrum. So kind of like a greenish yellow. But we don't see the sun as greenish yellow because it emits about the same amount of red light and the same amount of blue light. And you mix all the colors of light together, you get white. So that is why the sun looks basically white to our eyes. But watch what happens if something is a different temperature. Then that curve that shows what kind of light it emits will shift a little bit. If we get cooler, it'll shift to those longer wavelengths. And now you can see why a cooler star looks red to our eyes. Because in that visible part of the rainbow, it's releasing more red light than blue light. If you get cooler still, the star looks not only dimmer, but also more red, because now it really just emits red light. And even objects that don't emit enough visible light for us to see them that way emit some radiation. So we look up in the nighttime sky and we see our moon, we see the other planets, we even see the surface of the Earth through reflected sunlight. They don't emit any visible light of their own. But they can emit other kinds of light, like infrared light, right? That's just out beyond the red end of the rainbow we can see. And the gas giants in our solar system do that. So here's a real picture of Jupiter in infrared light. And you're seeing energy actually being released from the core of Jupiter. It escapes through the thinner parts of its atmosphere. So the gas giants, Jupiter, Saturn, Neptune, all emit more of that infrared light than they do, than they receive from the sun. So that's a little bit more on the cool end of the spectrum. But today we're going to get into the high energy radiation, the higher temperature objects. We're going to go out beyond the purple end of the rainbow into ultraviolet light. There's the curve for maybe a very hot star. It's going to emit more blue light than red light. So it looks blue to our eyes. But let's get out beyond the end of the visible rainbow. And let's start with ultraviolet light. And I'm just going to focus on one object here for this one. I'm going to try and find a certain star in the sky. I've left myself a hint on the screen here somewhere. I'll see if I can find it. Now, for the most part, you can still see a lot of the stars in the sky if you could see ultraviolet radiation, because they'd still emit it. But some stars would look a little bit different. And I am trying in vain to locate the one I highlighted for you. All right, here it is. Here it is. I see it. It may not look much different to you, but I'm going to try and get it centered there. And then we're going to zoom in. We're going to take a look at a star that's named Mira. And it's been long known to astronomers who watch the sky carefully, because even thousands of years, astronomers noticed that this star got brighter and dimmer over about 11 months, a little over 300 days. So it's a variable star, which is pretty interesting. But here I have overlaid a view from an old NASA spacecraft called the Galaxy Evolution Explorer. It used ultraviolet light to better understand other galaxies, but it made some other interesting observations in our own galaxy, like this view of Mira. Here you can see what looks like a long tail, like comets have, stretching out behind this star. That's most likely because the star is known to be moving pretty quickly along its orbit around the center of the galaxy. So it's moving through the dust and gas between the stars, the interstellar medium, and so it's creating kind of a bow shock in front of it, like a boat moving through water, and then it leaves a little wake, a little trail behind it, like a boat would as well. It looks pretty impressive in this view, but we can actually zoom out here just a little bit and get a little bit wider view, and we see the tail stretches out even farther. I won't give you all of the details involved here, but I will give you a couple of numbers. It'll be a little bit easier to explain if we see what's going on. So this is a variable star. It's a red giant star. And we know those stars, when they vary in brightness, they usually actually swell and shrink in size. So what happens when Mira expands, it's blowing out some of those outer layers of gas that interacts with the interstellar medium, leaves this long trail or this long wake behind the star as it travels. And because of the interactions between the gas blowing off of the star and the gas it's moving through, it creates this ultraviolet radiation that the Galax spacecraft was able to see. But it's the scales and the time scales involved here that I think are especially interesting. Thanks to the measurements of Galax, we know this tail is some 13 light years long. That is about 3 times the distance between the sun and the next nearest star. We also think that it's taken about 30,000 years for that tail to develop. So at the faint end of the tail, we're seeing gas was emitted from the star 30,000 years ago, which I think is a pretty impressive story. But there's actually more to this graphic. As I was researching the show yesterday and making sure all the graphics were right. This is an old graphic produced by NASA when the Galax mission was still in operation. And you may be able to read, if you're on a nice big monitor, that they put some important dates down at the bottom. So you get out to about 10,000 years. You're talking about the end of the last ice age. You get out to about 15,000 years. That's when they used to think the oldest human tools, human artifacts had been found in North America. But just yesterday, there was a news release, not really in my wheelhouse, but new artifacts discovered. They think that may actually move out to 33,000 years ago. So maybe the earliest humans in North America were watching this star change in brightness. And little did they know that we'd be able to see gas emitted from that star when they were first watching it, which is an even more impressive fact of the day, if you ask me. But there you go. There's Mira in ultraviolet light. Now, we're going to leave the ultraviolet part of the spectrum, but we're not going to leave this star behind just yet, because it has a few more surprises that are only really evident if you are able to see some different colors of light. So let's shift over to the X-ray part of the spectrum. And that is actually visible in ultraviolet as well. But in both ultraviolet and X-ray, we can see that Mira is not one star, but 2. So it's a binary star. The larger one, Mira A, is responsible for that long tail. But you can almost see a little bridge between those two objects in the X-ray view. And that suggests that this system is even more interesting than the ultraviolet light revealed. Well, let's go take a closer look and see what we may be able to find. So we've got 2 objects orbiting around each other. We're seeing some X-ray emission. That suggests that Mira, the supergiant red star, is orbited by a smaller companion, most likely a white dwarf. That's the kind of thing that the sun is actually going to turn into at the end of its life. And there's actually that little bridge that we were seeing in the X-ray view. There must be some material that's being pulled off of Mira A and onto Mira B. It's actually a pretty common thing for binary objects like this transfer of material, or this mass transfer. And when mass is transferred like that onto another object, it'll often get added to this smaller, more massive object, and we say it's being accreted, it's being added on. So the disk of material is an accretion disk, and as those accretion disks orbit around the object that's pulling in material, it warms up, and so you get higher and higher temperatures, you get higher and higher radiation. That's how you get the ultraviolet, X-rays, and gamma rays from these kinds of objects. Now we can actually see both the star and the white dwarf in this case. But such interactions can reveal objects that are impossible to see in any kind of electromagnetic radiation, and X-rays, like we saw here at Myra, were actually key to finding another elusive object. It's time to talk a little more about black holes. So let's jump back to the solar system, and I'm going to switch our view to be not visible light like we were all used to, but X-rays. And let's see if we can pick out some interesting features. Well, this brighter band must be the Milky Way. Just like it's a little bit brighter in visible light, it's a little bit brighter in X-rays just because of all of the objects arranged around the plane of the galaxy and the big clouds of dust and gas out there. Now, the especially bright spots that are colored yellow are going to be objects like these binary pairs we just saw at Myra. They can be supernova remnants, things like that. There's a little hot spot here. There's a little loop called the Cygnus superbubble. It is a big bubble of gas, probably blown out in an ancient supernova explosion, but there are a couple of other individual bright spots here as well. And one of them in particular is of unique interest. I'm going to try and get it close to the center of the screen for you. That is the location of Cygnus X1. It gets that name because it is an X-ray source, and it's in the constellation Cygnus. But its real claim to fame is what's here. So let's go take a look. Well, what we should be able to see when we get there is one super giant star. Now, this one is really massive. This one is something like 40 times the mass of the sun. And you can see it's a blue color, so you already know it's a pretty hot star as well. But if you watch carefully, you can see it's kind of moving through space just a little bit. Kind of looks like it's orbiting something. We've seen things like this with Pluto and Charon orbiting around each other. We've talked about other binary planet and star systems, and we just saw a binary star. But here, this one star is moving. We can't see anything that it's rotating around. If you do a little bit of math based on how the star is orbiting, you can figure out that it must be orbiting something that's about 14 times the mass of the sun, but we can't see it directly. We only see it through those X-rays, which suggests it's pulling a bunch of material in, incredibly high temperatures close to whatever this very compact invisible object is. So Cygnus X1 is the location of the first widely accepted black hole discovery. So here you go, a black hole up close. We see another accretion disk here. Instead of this leading to a star or a stellar remnant like a white dwarf, here it's simply a black hole. I actually had a leftover question in the inbox from a couple of weeks ago that I wanted to wait until we actually had a black hole on the screen to talk about. This question comes from Aparna, who asks, can a black hole be equated to quicksand for understanding? And, well, it's an interesting way to think about it, I suppose, but I don't know that I would make that comparison. Quicksand's a little bit different. Quicksand is actually a colloid, and if you want more details or more examples of colloids, I think just yesterday we released a video about making butter, and milk is actually a colloid as well. It's got milk fat suspended in a liquid, and that's a similar thing with quicksand. It's little particles, particulates of minerals. That's all sand is, suspended in water. And, you get into it, you can fall into quicksand and get stuck. So I guess in a sense they're sort of similar, but I guess the best analogy to use would be kind of along the classical lines that Einstein may have used. He talked about space-time being a material that could be warped and bent, and a black hole is just a super dense object that causes an extreme warping of space-time. So kind of the classical pictures of it is something like this. You got your black hole, and you've got this huge pit down below it. It's not really a material that you get stuck in. It's a change in the structure of space around you that you get stuck in. This view of it kind of makes sense to me. For some reason, I kind of like to imagine the black hole actually being at the bottom of this giant pit, because that's really what it's doing. It's stretching out space-time and creating this pit. Now, I've kind of drawn it here in a really simplified sense, limiting it to 2 dimensions, but you got to remember that it's warping space in all 3 dimensions. In any way you approach it, you can fall into it. So it's really hard to picture on the screen. I totally understand that. It can be really hard to give appropriate analogies. But I don't know, I guess if you want sand and rock to be involved, imagine instead walking along this rocky surface. You suddenly get to a sharp edge and you fall in. That's more what a black hole is to me. Going to be kind of hard to get back up to the top of the cliff once you fall in there. And a black hole is kind of the same way. You can get out of quicksand, but black holes not so much. So I hope that helps, Aparna. If you still have questions, or if anybody has questions about black holes or any other topics, as always, leave them in the comments, and we'll try to get to those. Let's see. I actually have another question in the comments, but it has to do with planets orbiting the sun, so I think I'll take a close look at it and try and answer it in a future show. We'll be talking about Mars next week, so that's a planet orbiting the sun. That'll probably work perfectly. Until then, let's see. Let's go back to the spectrum. Oh yeah, we've got one more wavelength of light to talk about here. Need to get on into the gamma ray part of the spectrum. So let's shift back home and let's take a look. Let's switch our eyes to work in gamma rays instead. Going to do this with a little help from another NASA spacecraft. This is the Fermi mission. That's been in space for over 10 years now, exploring in gamma rays and helping us map out the gamma ray sky. So that is what we are seeing here. Now similar to, say, the X-ray sky that we saw a second ago, a lot of those individual bright spots or nova eruptions, those can happen with the binary systems like we saw at Myra. You get too much material on the white dwarf, it can send up a little eruption of high-energy radiation, supernova remnants, X-ray binaries like Cygnus X1, things like that. That flat plane there is the plane of the galaxy, so then you get a little bit of gamma ray emission just from the big clouds of dust and gas out there, and of course more of those bright spots along the plane of the galaxy. A kind of an interesting thing starts to happen when people watch the sky like this and they see where all those bright spots are arranged. I mean, I guess we've been doing it for thousands of years, right? We go out at night, we see the stars, and cultures all around the world have played games of connect the dots, and we make the constellations up there. And now that we have these whole new views of the sky, we can create our own constellations in these other colors of light. And a couple of years ago, to celebrate the Fermi mission's 10th anniversary, scientists working on the mission did exactly that. They came up with their own unofficial, but I think pretty good constellations. They picked out some of those brighter points of light, those brighter sources their spacecraft were able to see, and they played connect the dots with them. Now, let's see if we can figure out what some of those pictures are. Well, that one looks pretty obvious to me. It looks kind of like a spider. Let's see. Oh, that looks like a hammer, maybe. That one, I don't know. That takes a little bit of imagination. Man, I don't know. Those are pretty tough. Kind of like the real constellations. Some of these are a little hard to imagine, but just like ancient cultures have told pretty elaborate stories about their constellations, they were able to concoct some pretty good stories about their gamma ray constellations as well. So now we might be able to recognize some of those. All right, we got Einstein. Ooh, Mount Fuji. That's a pretty good one. Oh, well, all right. I'd recognize that one anywhere. There's the Enterprise. Okay. Let's see. Looks like Captain Kirk needs to be careful because there's Godzilla. So a wide range of pictures you can imagine here. And it just kind of goes to show that maybe in the modern world, our modern constellations might take very different forms. And Fermi and observations and other wavelengths of light can reveal some unique things about our galaxy as well. Let me kind of zoom out here a little bit, and that's going to help all of us get oriented here. Let's see, I think I need to look along the plane of the Milky Way going in this direction. We've got a castle, we've got the Golden Gate Bridge. They even immortalized their own spacecraft in the gamma ray sky. All right, I think that is probably the brightest part of the gamma ray sky, probably the center of our galaxy. Now, if we ignore some of these bright sources in the gamma ray sky, we can just kind of see the gamma rays released by the thin clouds of dust and gas in our galaxy. And that would give us a view more like this. The color is kind of imaginary. They're just a sign to help us make sense of these invisible wavelengths of radiation. Now, the plane of the Milky Way is a brighter blue, and you might be able to pick out some big purple bubbles. They're actually extending out of the core of the galaxy. These are immense structures that were discovered by the Fermi mission. They're called the Fermi bubbles, believe it or not, and they're probably associated with that supermassive black hole at the center of our galaxy. We already made the journey to the center of the Milky Way at another show, but we see supermassive black holes in the centers of many galaxies. And in many other galaxies, we see that the black holes are more active than Sagittarius A star, the one at the center of the Milky Way. And some of them are shooting these huge jets of radiation into space. And perhaps these giant bubbles around the Milky Way are remnants of past activity around our supermassive black hole. Just like the motion of the star Mira can leave its traces across the galaxy in that long tail of UV radiation. Maybe these huge bubbles of gamma ray radiation are just reminders of a more active time in the black hole at the center of our galaxy. Pretty interesting thought, and might be interesting if that black hole got active again. Maybe we'd see those jets shooting out of the center of the galaxy again. But pretty unique discovery, possible only with gamma ray observatories, otherwise invisible to our eyes. Now, a lot of the bright sources in this view are long-lived phenomena, things that are always up there. They can always be seen by missions like Fermi. But that's not always true for sources of gamma rays. Sometimes the sources of gamma rays are only there for a very short period of time. They come and go in an incredibly short time scale. Sometimes you can only see them for days or weeks. And these are events called gamma ray bursts. And we've seen thousands of them over the decades. They were first observed in satellites in 1967. I believe it was. And since then, we've maybe gotten to the bottom of where some of these quick bursts of gamma rays come from. As an example, playing for you on the screen, this is a replay of what may have happened was observed a couple of years ago, using telescopes all across the electromagnetic spectrum, also observed in gravitational waves, a relatively new branch of astronomy, a merger here of two pulsars, creating a brief burst of gamma rays that was visible across millions of light years. So a pretty interesting event, and is the kind of thing that may be happening all across the galaxy all the time, and we observe them pretty often. Now, a lot of these gamma ray bursts we see, but because they're so short-lived, we can't study them in a lot of detail, and we don't necessarily know exactly where they took place. But here are a few that we can measure in decent detail, and we see that they are happening well outside of the Milky Way. So these are events in other galaxies spread all across the universe. And indeed, these gamma ray bursts can help us map out the locations of some of the most distant galaxies in the universe. And because we're now able to see the universe in all these wavelengths of light, and we can pick out objects at extreme distances, I think we're really ready to maybe complete the journey to the edge of the universe And that'll happen in a couple of weeks. As I've already promised, next week we're going to change our course just a little bit with all these missions launching towards Mars, and at least one lingering question about the solar system in the inbox now. We're going to head back a little closer to home. Next week we're going to focus on those missions heading to Mars this summer. Why are we so interested in Mars? Why do all these missions have to launch at the same time? Why didn't some of them launch last year? So we're going to cover all that in next week's show. Next Thursday, 2 o'clock Eastern Time, we're going to head back to Mars. Hopefully we'll have the Perseverance rover on its way as well. Its launch window opens early in the morning. I believe it is just before 8 o'clock Eastern Time, 8 a.m., July 30th. We'll have more details for you. We'll make sure you have links to be able to watch the launch for yourself. And then hopefully you can tune in to our show here for a recap next week. Until then, I hope that everyone has a great week. If you haven't seen Comet Neowise yet, it's starting to fade a little bit in the evening sky, but you may still be able to pick it out under dark conditions, low in the northwest just after sunset. Binoculars, telescopes, certainly going to help you out. It's getting in the neighborhood of the Big Dipper as well, so that can help you pick it out in the sky. As always, let us know if you've got any questions about this week's topics, random astronomical topics. Happy to take those on as well. So until next time, thanks for tuning in. Be safe out there, and I hope to see you again next week.